All right, so now we're going to start talking about how to kind of classify these vector spaces that we've been working with. So one of the ways we can do this is with a span. So we say that a set of vectors, v1, v2, up through vk, just any random set of vectors that already live in some vector space v. We said they span the vector space v if for every vector you can write that particular vector as a linear combination of v1, v2, up through vk. So if we just define, any random vector in v, we can write it as c1 v1 plus c2 v2 and so forth plus ck v sub k for some combination of c1, c2 up through ck. So pretty much what we have here is that as long as we're able to find these c's here, given the set of v1, v2 up through vk, then we can pretty much use this set of vectors here to describe the entire vector space. Okay, so that's kind of our goal here. We're trying to minimize the amount of information we need to give someone to describe our vector space. So the types of questions you'll be asked on an exam is to show that a given set of vectors, so you're given this, show that it spans a particular vector space. Other types of questions you'll be asked is if it doesn't span that vector space, does it span a subspace inside of that vector space? So it might be that you don't have enough vectors to cover the whole space, but you can at least get some part of it. And then the last type of question you'll be seeing is something along the lines of like, if you have a given vector space, tell me what you can use to span it. So determine a spanning set for that vector space pretty much from scratch. So we'll cover a few examples of questions you might see on an exam. All right, so as an example, we'll start with one of the easiest cases, is just to show a few vectors actually span a particular vector space. So we have 1, -1, 1, 2, 5, 3, and 4, -2, 1. So we have these three vectors here. We want to show that they span R3. All right, so the kind of confusing part is actually how you set this up. Once you set it up, you're good to go. But what we need to do then is we need to show that we need to use our definition. So we need to show that for any arbitrary vector v, I can write it in this form. So we're going to just define an arbitrary vector v in R3. I'm going to call it xyz because that makes the most sense. That's a 7. xyz. And I need to be able to write that as c1 times my first vector they give me, plus c2 times my second vector they give me, plus c3 times the third vector they give me. And really what I want to do is I want to show that as long as you give me an x, a y, and a z, I'm able to tell you exactly what c1, c2, and c3 should be so that I can write this as a linear combination. So our goal here is to figure out what c1, c2, and c3 are going to be. So that I'm convinced that we have a spanning set here. And this format here, it looks really familiar to us. We've been working with converting something that looks like this into a matrix. So I'm going to go ahead and skip that step. And we're just going to form this augmented matrix here with our spanning vectors as columns here and our arbitrary vector on the right-hand side of our augmented matrix. And what we want to do is we want to figure out what C1, C2, and C3 are, so we need to row reduce. And when we row reduce this, we have to make sure to be doing operations on the right-hand side as well. So for instance, my first operation will be to add this row to something. I need to make sure I add this y as well, okay? So I'm not going to waste your time in row reduce on screen, but if you do this a whole bunch of times, what you end up with at the very end is 1, 2, 4, 0, 1, 2 over 7, 0, 0, -23. The textbook always picks such horrible numbers sometimes. X, a 7th x plus a 7th y. And our bottom row here is 7z minus 8x minus y. So this is what happens when we row reduce this whole thing down. And I'm going to leave this negative 23 here because why not? But so now we have to figure out what C1, C2, and C3 are. And so what we can do is we can literally back solve this. So C3 corresponds to this column here. So I can write that C3 is equal to negative 1 over 23 times negative 8x minus y minus 7z. Okay, and remember that this x, y, and z, these aren't variables, these are numbers that you're giving me. So if you tell me to write some arbitrary vector here, as long as you give me an x, a y, and a z, I can tell you exactly what C3 is going to be in this linear combination. Same thing with C2. I'm not going to expand this all out or anything. C2 is just going to be equal to 1/7 x plus the 7th y, and then minus 2 over 7 times C3. And then C1 finally is x minus 2C2 minus 4C3. So the point here is that if you give me a vector here, x, y, and z, I can tell you exactly what C3, C2, and C1 are going to be in terms of those, such that I can write x, y, and z as a linear combination of these vectors. So there's no restriction on x, y, and z that I have to put in here, right? I'm able to put anything in and output a linear combination in terms of these vectors they give me. So at this point, right here, I'm good to go. We have that those vectors v1, v2, and v3 span R3. All right, so that's how you would do this. You would set up an augmented matrix, you would row reduce, you would check to make sure that there's no restrictions on x, y, and z, and you'd move forward. Another type of question you can come across is determine the span of a particular set of vectors. So it's not telling you to prove anything now, but now you're just given 3 vectors and you're going to want to figure out what they span. And 1, 1, 3. Okay, so we have the set of vectors. What we're doing now is we're trying to figure out what area they can cover. So at a maximum, they can be R3, right? So we have 3 vectors in, that's not a good way to do it, in R3. So the best we can do is cover R3 if we have a perfect spanning set. So what we're going to do again is we're going to define an arbitrary x, y, and z, and we're going to set it up as C1, 2, negative 1, 4, plus C2 times the second vector they give me, 3, negative 3, 5, and plus C3 times the third vector they give me, 1, 1, 3. Again, I'm aiming to solve for C1, C2, and C3, so I form the augmented matrix, negative 1, 4, 3, negative 3, 5, and 1, 1, 3, augmented with x, y, and z. And then I row reduce, and again, I won't do it on screen, but if you row reduce this all the way out, you get 1, 3, negative 1, 0, 1, negative 1, and then a row of zeros at the bottom. And then on the right-hand side, you get minus y, negative 1/3 x, minus 2/3 y. And then on the very bottom row, you get 1 over 21, again with the bad numbers, my bad, minus 7x, minus 2y, plus 3z. All right, so here we have our row reduced matrix, and there's something really important going on with this matrix. So here we have a row of zeros, and we know from chapter 2 that if we have a row of zeros at the bottom, we have a potential to have inconsistency in our solutions. And what that means is it's possible that we won't have any solutions to our equation. And that's not very good for us. It's also possible we have infinitely many. It all depends on what this right-hand side is. So this pretty much reads 0C1 plus 0C2 plus 0C3 is equal to something. Notice that if this something was anything other than 0, so if this was equal to 2, I'd have the equation 0 is equal to 2, and that's never true, right? So what I need to say then is I need to equate what's on this right-hand side over here to be 0, such that this will hold and I have consistency in my solutions, all right? So if you have a row of zeros at the bottom here, you need to make sure whatever on the right is also equal to 0 to maintain your consistency. So what we do then is we set 1/21 times this whole thing equal to 0. Since it's equal to 0, I'm going to get rid of this -21 here, or 1/21. And I'm left with this equation. So what this tells me then is that if I want to be able to describe a particular vector space with these 3 vectors that they give me, this equation has to be true of any vector in their span, which means that this is an equation of a plane in R3. So by taking, and I'll write this out, by taking linear combinations of V1, V2, and V3, we weren't able to get all of V3. We're only able to span a particular plane, which is given by -7x minus 2y plus 3z is equal to 0. All right, and this is where you stop. So you're done with the problem here. You've described the span of these 3 vectors, and you even gave a little bit of geometric interpretation because you know it's going to be a plane in R3. So this kind of wraps up our conversation with span. It's confusing in terms of differentiating between span and basis, so I do want to cover basis in a separate video instead.